Hello everyone, so in this video we'll be talking about the softmax function in PyTorch. So let's look into the documentation. As you can see, the definition is very simple, torch.nn.Softmax, and we have one parameter which is the dimension, and we are going to look into that. Now, how does softmax work? It applies a softmax function to an n-dimensional input tensor. Now I'll explain what that means and what is softmax and all of that. It also rescales them so that elements in the n-dimensional output lie in the range 0 to 1 and sum to 1. Now, what does it mean to say lie in the range 0 to 1? Doesn't this mean probability? Because probabilities lie between 0 and 1, and they also sum equal to 1. So basically what we are saying is we are trying to talk about probability. So softmax is defined as this function. Okay, you can see over here. So let's go to the board and see. Okay, so let's assume you have a neural network. Let's say you have any neural network of any dimension. So these are your neurons. Here also you have neurons. Any number of layers. These are all connected, and there are also some neurons here. All of them connected. Lastly, assume there are three output neurons. Okay, so these are the three output neurons. So let's say the output of this is called x0 because if you look in the documentation, it is given x of I. So let's say this is x of 0. Or let me just go this one step back, and this is x of 0. Okay, we'll show it by this way. Let's say this is x of 1 and this is x of 2. Okay, so these are your output numbers. Now for probability, there has to be two conditions that needs to be met compulsorily. Number one is all of the values are positive, and number two, that the summation of all of the x of i's for I equal to 1 to n, that is for all of them, has to be equal to 1. Okay, now how to get the first condition? So the function that we use is, we say we will exponent it. So we'll say e to the power x of okay, fine, instead of the top we'll write it in the bottom. Okay, from now on, so we'll say e of x of 0. So in order to make it positive, I have to say e to the power x of 1, and in order to make this positive, you have to say e to the power x of 2. Okay, so because we don't have any control over x0, x1, x2, but you know from the graph of the exponent function that it is always positive, right? It comes over here, it goes up and up and up and up. Okay, so you can see it's always positive, right? So this is guaranteed to be positive, and this is also guaranteed to be positive, which means our first condition is over here, first condition is met. Okay, now how to make sure that we get our second condition correctly? So can we say that if I sum all of this and divide each and every of this exponent by the summation, then what you're effectively doing is normalization. So basically what I'm going to say, instead of just saying e to the power x of 0, why not divide this entire thing by summation of e to the power x of I for I equal to 1 to n. Okay, so that is for all the e to the power x of I. And for the second one, we're going to say e to the power x of 1 divided by the summation again of e to the power x of I for I equal to 1 to n, and same for this also, e to the power x of 2 divided by x of 2 divided by summation of e to the power I, e to the power x of I for I equal to 1 to n. Hopefully you get the idea. Why? Because if you sum all of this, what will happen is the sum so if you sum all of this over here, let's see, so the denominator remains the same, that is e to the power x of I equal to 1 to n. But if you add all of this, you will get nothing but e to the power x of I equal to 1 to n. So this and this will get cancelled, everything, and finally you will be left with 1. So this is the idea. Okay, so the second condition, that was summation of everything equals to 1, is also satisfied. So first is also satisfied, second is also satisfied, which means now this is a valid probability distribution. Now one thing that I need you to understand is, here we gave only one example. Let's say that let's say we were dealing with iris dataset. Okay, so in iris dataset, what you have four features. You have sepal length, you have sepal width, you have petal length and petal width. Okay, so basically there are four features over here, 1 2 3 4, and output and a number of to say rows, you have 150. Here in this case you gave only one row, and let's say these were 4 input neurons or whatever, 5, you gave 1 cross 5. So this is 1, this is 2, this is 3, this is 4, and this is 5. So you give 1 is the number of examples and 5 is the number of features, right? And lastly you got 3 out of it. So the answer was 1 cross 3, because number of examples have not changed, but obviously since there are 4, or since there are 3 neurons, you're getting 1 cross 3 or 3 as output. What if you have n over here? You give n examples, and obviously each example is of 5 because there are 5 neurons over here. Or if you were using what to say, iris data set, this would have been 4, but since I have shown 5 neurons over here in the starting layer, you have n cross 5. So what do you expect the output dimension to be? It is going to be n cross 3, which means you can always represent the output in a matrix. Okay, so the way I'm going to do is I'm going to say n rows n cross 3. Why? Because every row is an example, and in each row there are output of 3 neurons. So x1 x2 whatever, x1 x2 x3. Same thing for the second row, you'll have x1 x2 x3 and so on and so forth for n rows. Okay, now let's look into now how we are going to apply the exponent over here. So exponent is simple. Just let's say this matrix is act. I'm just calling, you can call it A, B, but since this is from the final layer, we are expecting this to be to be having, let's say, you can say even A, doesn't matter, okay? Because Softmax is also an activation, right? Softmax is an activation, so we'll apply it later. So let's just call it A. So the first step, what I told you, you have to exponent everything. So can I say the first step is basically exponent of A, right? And then you have to understand that how do we want the softmax to be? We want the denominator, right? The denominator was basically summation of e to the power x of I. So we have got e to the power everywhere, but when finding the summation, that is summation of e to the power x of I, we need to go only this dimension. Why? Because these are the output of neurons. If you go over here, basically you are taking an average of, if you're taking here, you're taking the average of the first neuron across all samples. But what if you have only one sample, right? So this does not make sense. What you want is, you want for all the neurons, you want to take an summation of the exponent for all the neurons. That's why you are saying this. So the way you represent this in PyTorch is by saying in Softmax dimension equal to 1. Why? Because we are doing across columns. Across columns, so dimension equal to, so always remember, for rows it's always 0. For column dimension, for rows dimension is always 0. For column dimension is always 1. Since we are doing softmax across columns, we are saying dimension equal to 1 because column is 1. Okay, across what? Across columns. Okay, so if we were to do across rows, I would have said dimension equal to 0. Okay, but since we have to do across columns, we will say dimension equal to 1. I hope that part is clear. So what is dimension? I explained over here. Dimension is basically across what you are doing, across which dimension you are doing. You can see a dimension along which softmax will be computed. So across, along, doesn't matter. Okay. Return type is none, not required. So what it returns a tensor of the same dimension with the I have explained you. It will be a probability distribution. Okay. So let's see some code over here. So I had already run this code, but I'm going to do it one more time for you. So these are the basic imports. You are importing torch and torch.nn. Here I am having a random generation of values. Okay, let's assume this is our A matrix and it is 9 cross 10. So what is 9 over here? Okay, so if this is our matrix, so let's assume that we have a matrix over here, and it is said that it is 9 cross 10. Which means these are 9 columns. What does 9 rows? What does 9 rows represent? 9 examples. Okay, 9 examples. And it says 10 columns. So what it means is there are 10 number of neurons. Assuming this is a simple neural network. Okay, so 1 2 3 4 5 6 7 1 2 3 4 5 6 7 8 9 10. Okay, so there are 10. So 1 2 3 4 5 1 2 3 4 and 5. So there are 10 columns over here and there are 9 rows over here. So 9 cross 10. Where do you want the softmax? Obviously for each example you want the softmax, right? So you want softmax to be done over here. So obviously first the exponent has to be done. After that you want the softmax over here. So this is across columns, which means dimension equal to 1. Okay, so over here let me go and print those. So you can see over here there are 10 numbers in the row. Okay, you can count over here. And how many rows are there? So this is the first row, this is the second row, this is the third row, and so on. You have 9 rows in total. Okay, now I have explained that you have to use nn.Softmax with dimension equal to 1. Why dimension equal to 1 I have explained. And on what? On the rand variable, because rand is basically a random number generation. So we will calculate this over here and you can see that we have gotten these numbers over here. Okay, so let's verify. So if this were to be true and softmax is applied in this dimension, which means the summation of all the values that we get after the, let's say this in this matrix, this is where you have applied the softmax. Okay, so it means that we have taken the normalization across this dimension, which means across this dimension the sum should be equal to 1, right? Because it has been normalized. So I am going to just verify that. Okay, so dimension equal to 0 should not give you, because dimension equal to 0 is through the rows, but we want it through the columns. So I'm saying out dot sum, out, which is the output that we have got over here, output of this, the softmax. If you want to sum it across which dimension? Dimension 1. I should get all of them as ones. Okay, so let's go and see. You can see all of these are ones. Hopefully you understood the idea, right? So this is mostly for checking. You don't need this. Okay, so is there anything that I have forgotten? I think I have covered everything in this. Okay, all these things is not required. NNL laws, we might do it some other day, but it's we generally not use it. Log softmax, it is just you take one more step, you do one little change and they just give another name. It's nothing fancy over, there's nothing fancy over there. Okay, so just a small recap. Okay, I hope you have understood it already, but just a small recap. You have some neural network, it has some output layers, you are giving n examples. It is let's say these are n cross 4, this is 4 and this is 3 over here. So your input is n cross 4, n is examples, number of input features, and then finally you will get the same number of n cross 3 over here, same number of examples, but since there are 3 neurons over here, you have n cross 3, so you get a matrix of n cross 3. Okay, then this represents your again number of examples, and this represents your output neurons. Then what you do, you use a simple exponent, and then you use after using a simple exponent, you normalize along this dimension. Okay, across this columns, which means dimension equal to 1. Okay, and then finally you get these values, and these values will later be used with cross entropy for finding loss. Not this is beyond the scope of this video. So I hope you understood what I have taught you today, and if you like the video, please like and subscribe. Thank you very much, and bye.